Thank you, Laura. It's a pleasure to be here. I also want to express my thanks to Steve and Sylvia. I had some of the same experiences that Laura did, being invited to dinners over at Steve and Sylvia's. But in addition, I remember when I first came to UW, my office was just a couple doors down from Steve's. And Steve used to drop by my office quite regularly, a couple times a week at least, with all kinds of tidbits of advice from the old and wiser professor to this youngster. And I have to say that being young and full of myself, I ignored every single one of his suggestions. Aside from giving me advice about teaching, he also gave me advice about what stocks to buy, and I ignored that advice as well, which occurred to me this week that that is probably why I'm giving the lecture, but Steve and Sylvia are endowing it. So I want to thank you for that. I've attended the Burgess lectures before and have been really impressed by them. I hope to do honor to that tradition. My talk's going to be a little bit different from the ones that have come before. The previous speakers have tended to talk about what's going on that's important in their field more broadly or give some historical perspective. Mine's going to be, frankly, more personal and unabashedly so. I think this is because I did recently retire and I just feel some urge to give something of a valedictory, just to look back on my career and tell you a little bit about how I got through it and what was most exciting to me. But also, I hope to make this talk a tribute to my colleagues, both on the faculty and the student colleagues who were so very important to any successes that I had. And just wanted to acknowledge their contribution. And so this talk is going to be really about what I did as an advisor and what my students did as the real workers. And with that, let's get started. Stating something that we all know, population growth, pollution, climate change, and urbanization are stressing water supplies throughout the world. There are places where water is becoming scarce, where people are having to use water that is of much poorer quality than it used to be, either because of tons of algal growth or because of other pollutants in the water. And if you've been keeping up with the news lately, I believe we're for the first time in history in a situation where in a first world country, there is a major city whose taps may not produce any water when they open them in a few weeks. Of course, water engineers have been aware of this situation for a while and have been doing whatever they can to improve the production of clean water from more challenging sources. And by far the biggest improvement that has been made, I would argue the biggest improvement in water treatment since chlorination was first introduced in the early 1900s, has been the introduction of membranes to remove contaminants from water. This upper diagram shows the municipal membrane system sales over the past 15 years. You see this is in dollars. It went from about $750 million 15 years ago to a little over $2 billion a couple of years ago. And this growth is continuing to be exponential. And this is just the sales to municipalities. In addition to that, of course, there's a great deal of money being spent on operation. And this trend, I expect, will continue for the next several decades because even though everybody recognizes the need for improved water treatment, the fact is that water treatment plants are built to last for many decades. And so there are, even though the newer plants that are being built are almost entirely designed around membrane technology, there are still a lot of older plants that don't have that technology and will continue to be upgraded over the next few years. This is what membranes look like. This is a small-scale laboratory system, and this is a larger system that's being installed in a wastewater treatment plant. Both of these show you, it's a little bit hard to see, but membranes, as they are used in practice, are like little straws, actually tinier than straws in diameter, but longer than straws. And the straws are made of somewhat permeable material. So water, dirty water, is either introduced on the outside of the straws and then is sucked through the straws. The clean water is sucked through the straws, and the straws reject the contaminants, or things go the other way. The dirty water is put on the inside, and the membrane takes the contaminants away as the water is pushed through the walls of the straws. The problem with that is that the contaminants which you want to remove, and which the membranes do a very good job of removing, clog up the holes in the straws. Right? So the very job of doing what the membranes are supposed to do causes them to fail. And that failure is called membrane fouling. This is a water that we've used, a bucket of water that we've used for many years in our testing. It's from a local lake, but one that is fairly severely impacted. It's dirtier water than most drinking water supplies would be. We used it so that we could do our experiments faster, to be frank about it. But the general kinds of contaminants that are in this water, primarily stuff called natural organic matter, is the major foulant of drinking water membranes. Now, as stated here, membranes are already widely used in water treatment, but their efficiency and even wider application is being limited by fouling, and natural organic matter is a major foulant. Not only is it a major foulant, but natural organic matter also reacts in traditional water treatment plants to form chloroform and other carcinogenic compounds. So you want to get the organic matter out of the water, and membranes do an okay job of that, at least some do, but you want to get it out without causing the membranes to get fouled. Now here are the membranes that we actually used in our testing, at least what we started with. We use much smaller membranes and open membranes for two reasons. One, just so that we don't have to truck tons of water into the lab, and secondly, so that we can see what happens. So that this is a membrane, this white circle here is in a cartridge. We push water through from the top to the bottom. The membrane collects the contaminants and also gets fouled, and we measure that fouling. And this is something that I'll show you later. This is a different kind of membrane. It's one that's used and sold to the military and to outdoor enthusiasts to take into the outback. And you can use this to filter your drinking water if you're at a place where you're taking water from a natural stream that might be contaminated. So these are small things that we use in the lab, and I'll talk about those as well as some of the larger systems that we study during the rest of the talk. Now here's what happens during fouling. Here again is the same water. This is a clean membrane, and these are pictures of the membrane after some water has passed through. This occurs over the course of a few hours, and you can see the membrane gets discolored, and that discoloration also plugs up the pores. This is a higher magnification diagram or image of the same membrane. We didn't get a good image of the membrane here, but this is the clean membrane. You can see all the little holes in it. These holes are just a few nanometers in diameter, so they're very, very tiny. You can't see them with the naked eye, but with a scanning electron micrograph, you can see it. And after 1 hour, you can see many of the holes are partially plugged. After 2 hours, most of them are plugged. And after 4 hours, they look completely plugged. And the impact then is shown here. Again, I have the same images up here as before. And this graph is showing the resistance to water flow. This tells you how hard you have to push to get the water through the membrane. And when the membrane is clean, as is shown by the blue line and the picture up here, the resistance of the membrane, we don't have to worry about the numbers here, but the resistance is about 0.5 by 10 to the 12th in these units. That's how much the resistance the membrane applies to prevent water from going through. And the red curve here shows the added resistance that's caused by the fouling material as it accumulates on the membrane surface. And what we can see is that after just about a half an hour, at the point when the membrane looks like this, the contribution to fouling or to resistance caused by the contribution to resistance caused by the fouling material is about as big as the original resistance of the membrane. So together, that means the resistance has doubled. And as you go up to 2 hours or 4 hours, or I guess it's 1 hour and 2 hours, the resistance gets to be much bigger by the fouling material than by the membrane itself. Okay, so the fouling's a big deal here. Now, the other thing about this is that these particular membranes, which are really used in water treatment do not collect very much of the NOM. So even though they foul very badly, they're doing that by removing less than 3% of the natural organic matter from the feed. So it's a lose-lose situation. You're not getting very much of this stuff out when you want to get it out, and the little bit that you are getting out is causing problems. So this is what we want to overcome. The second thing to note is that when the NOM sticks to these membranes, it's very difficult to get it off. The way membranes are normally cleaned is by pushing clean water backwards through the membrane every once in a while, usually every half hour to an hour, so somewhere around here to here, to try and clean the membranes and get that accumulated foulant off of the surface. But the NOM by itself sticks pretty tightly. So here's what happens. Of course, engineers have known this for a long time, and what they do is they add chemicals to the water in order to try and get this NOM out of the water before the water is applied to the membrane. So here's the raw water again, and they add alum as the most conventional chemical to add. When they do that, the alum forms this hydrous, gelatinous group of particles, chemically called aluminum oxide, and these particles are hydrous, that is, they have a lot of water in them, and they're sort of fluffy, and they happen to have a very strong attraction for this natural organic matter. So they do a good job of collecting the organic matter, and then you mix all that stuff up for 30 minutes to make sure that all the water is contacted with these little particles, and then you let the particles settle out, because you don't want to apply them to the membrane, so most of the particles settle out, and then you take this water that's up top and you feed that to the membranes, and this is a full-scale membrane plant. And so this water is what's going into the membranes, and although it does have some new particles that it didn't have before, it also has less fouling organic matter, which is a good thing. Right? Now, this is important. You're going to have to treat the water for at least an hour, hour and a half, maybe more than that, in order to get it clean enough to do the job that you want it to do. Well, so there's two problems now with this conventional treatment. Again, here's the membrane plant. This shows the pressure. This is a measure of the resistance. The higher the resistance, the higher pressure you need in order to push the water through. So what happens is that, and this is, by the way, is made-up data. It's just for illustration. But what we see is that when the membrane is first used for clean water, there's maybe a pressure of 2 to 3 pounds per square inch. And over the course of the next 40 minutes, the pressure builds up because of the accumulation of material. Well, I said that the NOM has been taken out, so what's causing this? Well, it's a combination of the residual NOM and the particles that didn't settle. So now the particles are acting as the foulant along with the NOM. And you can ask yourself, well, if you're just taking one foulant out and putting another one in, what's the point of this? The point is that when the aluminum oxide and the organic matter are mixed together, those particles that get in there, even though they do cause fouling, they're much easier to wash off. And so when you wash them off, the pressure drops back down close to the original, and then you go through the same thing over and over and over, and you don't get all of them out, and so the pressure does gradually build up over time, but nevertheless, it's an improvement over the operation if you don't have the pre-treatment, the treatment with the chemical, okay? And then after a while, the buildup is too severe and you have to do a more extensive cleaning, and that's what allows you to come back down almost to the original pressure, and then the whole cycle is repeated. I've shown this. This is a real representation of what happens, but it's very compressed. The truth is that these cycles happen every 30 to 45 minutes, but the buildup here takes maybe days to weeks, and so it's only every couple of weeks that you really have to do a very extensive cleaning. Right? Now there's another problem, aside from the fact that the aluminum causes fouling, it's that here's the settled stuff. When this stuff settles, you still have to dispose of this. You got a sludge, a water treatment sludge, that you have to get rid of, and you that's taken to a landfill. And that turns out to be quite a pain to do, because remember, that sludge is very hydrous. The aluminum absorbs a lot of water, and it's really hard to get that water out. And as you can see here, this is what that sludge looks like. It looks like oatmeal, okay? And the thing is, if you try to drain the water out of that, you can't do it. that stuff is so thick that you just can't get the water out. So you end up taking a ton of water to your landfill along with the solids, and that's very expensive. Or you end up spending a lot of money to dry the sludge by heating it. Either way, that's not a very good option. So we want to overcome those problems. Oops, sorry about that. All right, so an overview of what the problem is and where we're at. You can treat drinking water directly by membranes. You don't remove very much NOM, which you'd like to remove, and you get rapid fouling, some of which is irreversible because you can't get the contaminant off of the membrane, and you need to clean it frequently. If you go to conventional membrane treatment with alum, the alum will collect some of the NOM and remove it, and it mitigates fouling by the NOM. But the alum becomes a foulant, and frequent backwashing is still required, and it generates a thick and problematic sludge. And so our goal in our research was to develop a material and a process that would do three things: remove at least as much NOM as the conventional process does, dramatically reduce fouling and backwashing requirements, and generate a sludge that's easier to handle and cheaper to process. And so here's what we did. We first started with those conventional particles. We take alum and we just add them to water, and we get exactly the same hydrous particles that I mentioned earlier. But then we decided to heat this water, with the idea being that if we heat it, we could drive the water out of the particles. So instead of being these gel-like particles, the water would get squeezed out by the heat, and the particles would have different properties, and we call those very creatively HAOPs, or HAOPs, which is heated aluminum oxide particles. We're very proud of that. Okay. Now, what do these particles have that's important? They have a particle size that's small, that's important to us, but I don't want to go into that in detail. But the main thing is that they, in fact, do become small, and they're like tiny, tiny pieces of sand, okay? Which is very different from the material we started with. And what does that do for us? Well, our hope was that if we compare the aluminum flock, which is gelatinous, with the HAOPs, which are more like microsand, this is what would happen when you apply them to a membrane. The gelatinous particles, we know, come down here and they form a jello-like layer on the membrane, which is very hard to drain. Whereas our particles would form layers of sand-like, like a sand layer with openings between them that would not be compressed, and so the water could easily flow between these particles and not get hung up in the sludge. So the next thing we did was said, well, what if our particles don't collect NON anymore? So we tried it, and honestly, this was pure luck, but it was good luck for once. We found that the HAOPs actually absorb more NOM than these conventional alternatives. Here's alum, but here are the two other things that are most often used: an iron compound and activated carbon. And although activated carbon does collect more organic material than HAOPs out at these high doses, this is the dose range where you want to be in. And under those conditions, we found that actually heating the particles made them better at collecting the organic matter. So that was exciting. And so then it was time to do some experiments. And here's what we did. I have this up here as the cartoonish version of the conventional treatment, where you mix the alum that forms these circles that are meant to be the aluminum oxide. Those particles collect some of the organic matter, which is represented by the little squiggles. You settle it out and take that out, and then you put water onto the membrane that still has a little bit of NOM and a little bit of particles, but not a lot. That's the conventional process. We said that now that we can make these sand-like particles, we don't have to do that. We can put a whole bunch of aluminum onto the membrane to start with, and then just apply the water directly without ever adding the aluminum to that. That has two advantages. One is that the water gets exposed to a higher concentration of particles. Even though we're only using the same amount of particles, we're putting it all in at once, and we can do that because it doesn't plug the membrane. And secondly, we can shorten the contact time, because when this flows through here, it's going through a layer of particles that's like sand, and the organic matter is right up against the sand. It has to pass through the sand like this, so it's very in close contact with the removing agent, and so we don't have to mix everything together and wait for the particles to find the NOM, right? So we did that, and here's how we did it. We took the HAOPs, and we applied them. Here's our little cartridge, and here's the cartoon version of it. And we applied the HAPs to the cartridge, and we made a layer on the membrane. And then we took water from Lake Union, here's Lake Washington, and passed it through that. The first layer, the first step, the layer of HAPs, the deposition of HAPs, takes just a minute or so, and then we can do this for a few hours and see what happens. And here's the result. First, again, for reference, here are the pictures before of what happened to the membrane when we applied the water to it, and we saw the discoloration. Here's what happened to the HAPs that are on top of the membrane when we did the same thing. This is the clean HAPs, and this is the coloration that occurred, that developed over time as we passed more and more water through. And the intensity of the color is an indicator of the amount of NOM that has been removed. And you can see that these things did a great job of removing that organic material. It just kept collecting and collecting and collecting. So we can collect a lot more NOM here. And on top of that, the resistance to flow through here remains relatively low because of the separation of the particles. The next slide shows this resistance again, where again we're looking at the pressure needed to push the water through, but now we're pushing it through both the layer of HAPs and the membrane, okay? And this is the volume treated per unit area of membrane. Again, this is roughly an indicator of time of the experiment. And we did it three ways. We did it first just like the upper images on the previous diagram, where we applied the water directly to the membranes, didn't have any chemical dosing, and the resistance built up very quickly. That's this curve, okay? That's over maybe a half an hour or so that this pressure built up that much. Then we did conventional dosing and settling with alum, the standard treatment. We added the alum to the water, we mixed it, we waited 2 hours, then we took the clear water and applied it to the membrane, and we got this curve. And it's still pretty steep, but you see, it's a lot better than not adding the alum. We've gone about twice as long before the pressure builds up to any given level. But when we took the same amount of aluminum and we made it into HAPs and we put those on the membrane and saw what the pressure profile was, we got this. It took almost 10 times as long before the resistance built up as high as it did in the conventional system. So we have two very good results here going back: higher removal of organic matter and much slower fouling of the membrane. So we're making good progress here. And so here's an interim summary. This is after, I don't know, 5 to 10 years of the research. We found that membrane fouling can be severe despite removing only a tiny amount of the NOM, 3, 5, sometimes 10%. HAPs are excellent collectors of organic matter, at least as good as the gelatinous aluminum oxide. And HAPs layers are incompressible, and therefore they're hydraulically conductive, which is another good feature. Predeposition of HAPs protects membranes from fouling much more effectively than conventional processes do. This is all well and good, but we have one other thing that we haven't tested at all yet, which is that a successful process requires that the HAPs be deposited, and then eventually the HAPs do have to be thrown out, just like the aluminum oxide from a conventional process. Those particles get clogged up with organic matter, and they have to be removed from the membrane, and a new layer has to be put down. So the question is, can those HAPs that have been deposited and have been collecting all that organic stuff, can they be easily washed off and a new layer put on, and washed off and a new layer put on over and over again for years without fouling the membrane? Okay? So to do that, we had to design a system that was easy to use to clean out the HAPs after we were done. We couldn't do it with those little membranes because those have the consistency of sheets of paper. You can't pass water quickly through them to wash them off the HAPs. They'll just tear apart. So we moved to a different kind of membrane, the one that I showed you earlier that is used by hikers. And we put that in a column here, and we did the same 3 experiments. In the first experiment, we just took lake water and we passed it through this membrane, and the water comes up goes through the membrane, gets collected out here so we can determine how much NOM was removed. We can keep track of how hard it is to push the water through. And that's the baseline case, the control for a system that has no chemical treatment. And then we did 2 other experiments where we did the same kind of thing, but we did more conventional treatment. After taking the water, rather than feeding it directly to that membrane, we first added either alum or HAOPS. We did it 2 separate times. Once we added alum to simulate a standard process, and then we thought, well, let's just try adding our HAOPS directly the way alum is added and see how that works. So we did both of those things, and after doing that, we measured the, we recorded the pressure required in those 3 cases. In the control case, where there was no alum or HAOPS added, the pressure built up like this. And again, this is over the course of several hours. Right? And this, I'm sorry, I forgot to mention that at the end of each step here, which was after 2 hours of filtration, we pushed water back through the system from here inside. That broke the HAOPS off of the surface of the membrane and flushed them out, and then we put a new layer on. So we did that every 2 hours. We cleaned that membrane. And that's what these data points are. This is the pressure at the beginning of the next step after using the membrane for 2 hours and then cleaning it. And what we see is that the addition of either alum or HAOPS does a good job of improving the performance compared to not adding them, and that HAOPS and alum perform about equally well. One can argue that HAOPS is a little bit better here because it took a little bit longer for that pressure to build up, but it built up anyway. Now remember, this is not the process that we want to use. This is a process where we used HAOPS in the way that alum is used. Right? Then we did the other experiment, the one that we wanted to try, which is the same thing, but now rather than adding the HAOPS or the alum to the water and mixing for 30 minutes and settling for 2 hours and then applying the water to the membrane, we first just put the HAOPS directly on the surface of the membrane by using our stock solution, pushing it through here, and as the water is pushed through the membrane collects the HAOPS and a layer forms there just like it did on the previous membrane. And that only took 10 minutes. And then we fed water from the lake through this, and in order to get out now, it had to go up through, and to get to the membrane, it had to go through the HAOPS layer. So we did that. You remember, let me just, what the 3 curves looked like before for when we did the conventional treatment. Here's what it looked like when we did it that way. And this one, we didn't clean that membrane every 2 hours. We cleaned it basically once a day, every 22 hours. So, and over the course of 3 days, there was effectively no fouling. There was no buildup of pressure. In other words, we can use our HAOPS now to do the same kind of job that conventional treatment accomplishes, with much less fouling, with a much shorter time of treatment in the treatment plant, only taking 10 minutes for the HAOPS to be deposited as opposed to a couple of hours for the water to be treated. And we can do this with very little pressure buildup over days. And in terms of the NOM removal, again, we have here the 4 conditions. This is now shows the amount of NOM that came through the membrane that was still in the water after being treated. If we didn't add any chemicals, it was 90% still in the water. It was 10% removed. If we added alum, it was about 45% removed. If we added HAOPS in the conventional way, it was about 50 to 60% removed. And when we had the layer of HAOPS on the membrane surface, it started out at 80% removed, and at the end of a day, it was down to maybe 70% removed. So this was just win-win. We were getting lower pressure, higher removal, everything was looking great. And now this shows you what the sludge looked like when we backwashed the HAOPS out of this filter. Here's the clean HAOPS that we started with, and sure enough, just like before, those HAOPS had collected a lot of the brown gunk that we're trying to get out. Well, we wanted to see, remember there were 3 goals. One was to remove NOM. Second was to reduce the pressure buildup or the fouling. The third was to get a sludge that was easier to dewater, to get the water out of. And so we took this stuff and we passed it through a filter, or we applied the mixture to a filter to see how hard it would be to get the water out of that. And we got a nice little muffin. Water just drained right through this stuff. It was amazing. This turns out, this is not what I understood at the beginning of this research, this turns out to be perhaps the biggest cost savings for a water treatment plant that our process might be able to provide. It is so expensive to dispose of, to dry and dispose of conventional sludge, that just getting a sludge that is this easy to dewater may be the biggest advantage of our whole process. So at that point, we asked ourselves, now let's step back and think, what do the HAPs do in this process, and what does the membrane do? Well, the HAPs layer removes the NOM and mitigates fouling. That's great, okay? The membrane itself is basically just holding the HAPs in place, and it also removes very small particles that sneak by the HAPs, because the holes between the HAPs, the spaces between the HAPs, are bigger than the holes in the membrane. So we still want to remove things like viruses from drinking water, and the HAPs don't do a good job of that. So the membrane is a backup that gets those viruses out. But the nice thing is that now the HAPs are removing the stuff that causes problems for the membrane, and the membrane, in a sense, is allowed to concentrate or focus on just those things that it removes best. So we asked ourselves, does it really make sense to use the membranes to hold the HAPs? Maybe we can be better off by separating the units and optimizing each part for its own application. And so with help from some industrial partners from downtown, we came up with this idea. We took a mesh, and I have it here. It's like a piece of fabric. It's still about the thickness of a sheet of paper. It's good and strong, and it has openings that are about 5 microns, which is small enough to capture the HAPs. And we put that on a backing, a plastic webbing that we rolled into a tube. So this, I don't know, didn't have any of the webbing in the flat sheet, but we took this, we placed it on the webbing, and then we rolled the webbing to make a tube. And so we now have this stuff in a tubular form, but it's, the webbing is providing the structural support for it. Okay? And we thought that will capture the HAPs, and then we can take the water that comes out of that and apply it to the membrane, and now there's going to be no HAPs directly in the membrane. So here's the real system. This is the tube I just showed you. The water is going to come in this tube. We're going to put the HAPs on this tube. The water is going to come through here, go through the HAPs, through the mesh, and then go into this, this ceramic membrane. Okay? So here's the cartoon again. You're used to seeing this now. Here's the system in reality. Here are the HAPs. We first take the HAPs, we apply them just to the mesh, and the water that comes out, we just throw out. This again takes 10 minutes or less. Then we take water from the lake, we pass that through the mesh and the HAPs, and then apply it to the ceramic membrane. Okay? And see what happens. Well, as before, the HAPs themselves do collect NOM, and they therefore do get a little bit plugged up. All right? This shows about 10 days of operation, and with this unit being cleaned about once or twice a day. And each day, the pressure builds up a little bit, and then we clean it, and it comes down again. And then it builds up a little bit the next day, and we clean it. And so we have 10 days of cycles where the pressure, in order to force the water through this system, is building up on the mesh, and then we clean the mesh, and it doesn't have any HAPs. We put a new layer of HAPs on and start again, and that works fine. So this shows a pretty good consistency, and the pressures here to push through the mesh are actually lower than what we had for the membrane because the openings in the mesh are bigger. Okay? Then comes the more amazing part. During this whole time, we cleaned this mesh once to twice a day, but we never cleaned this membrane at all. We just took the water out of here, and 24/7 we passed it through this ceramic membrane. Most of the fouling material has been removed here, So look what happened. The pressure buildup on that ceramic membrane was essentially zero. And I'll tell you two brief stories about this. I showed this to the funding agency, the Office of Naval Research, and the guy who was in charge of providing the funding said, wait a minute, let me get this straight. You did this for 10 days without ever cleaning that membrane, and you didn't see any pressure buildup? I said, that's right. And he said, for 10 days? I said, yeah. Without any pressure buildup? Yeah. And no cleaning? I can't believe it, all right? But he wasn't even the best. The best one was a Polish postdoc I had working with me at the time who loved American colloquialisms. And she usually got them right. She usually did. But sometimes she didn't. And she came to me and she said, this result it's amazing. It's astonishing. It's blow-minding. So I love that expression. All right. So where are we now? We have minded our blows or blowed our minds or whatever. And we've gone from this scale to this scale to this separate treatment. And all's looking good. But these were all laboratory systems that we needed to do to prove our concept and to make sure that we had something that was even worth taking to the next stage. And we were very pleased about this, but this honestly was probably 15 years. I've skipped a lot of stuff, as you can imagine, and most of it was failures. But I wanted to show you here a higher magnification version of the surface of this tube, because I hope you can see that these little bumps in the middle are the mesh sticking out. And all this other stuff is the webbing that's holding it. And the truth is that that webbing takes up about 25% of the surface area. And we don't want that. Membranes are expensive. These systems can be expensive. And we don't want to block 25% of the surface area by the plastic. On top of that, the whole process of gluing the mesh to the webbing was a pain in the butt, frankly, but we can do it for this scale system. But we talked to our industrial partners, and they said they couldn't think of any decent way to manufacture this at mass scale. We just weren't going to be able to do this. And again, this going from here to here was a few years. We tried all kinds of things. And one day, we just had an epiphany. We said, because we kept thinking, how are we going to hold the mesh in place? Because we needed it to be structurally supported so that when we backwashed it, it didn't collapse on itself. And then all of a sudden, we had this, I say, epiphany, that we could find mesh tubes that were already made into tubes that were actually even smaller than this, and we didn't have to connect them to anything. We could make them, put a core through the center of them that was smaller in diameter than the mesh tube, and then we would glue this mesh tube or otherwise attach it to this end piece. And what happens then? If we now put the water up through the middle of that tube and put the haps on that tube and we expand it, we apply pressure to push water through, that mesh would form a taut cylinder and it would be separated from the core. And so all the surface area inside the tube would be accessible to the water. There'd be nothing blocking any of the tube. Water could come up through there and then go out through the tube using 100% of the surface area. And then when we needed to clean it, we would push water in from the outside, but it wouldn't collapse on itself because we could put a core there that had ribs so that the ribs would catch the mesh and there would be channels between them, and the haps then would flush out with the water and come out of the system, and we could take advantage of that and make the whole system, as I say, accessible to the haps and to the water. So, coming to the end, we got to the point where it was time to scale up and start thinking about industrial-sized processes. So we built this 6-tube module. As I say, up until then, this was the biggest thing we had built. These tubes, we have 6 tubes in here. They're about 2 foot length each. And so they have a good deal more water processing ability than this. We use them to treat water, and this is, hot off the presses. I want to show you the result. I didn't make this up. This is yesterday's result, okay? This is the water. Now, this is Lake Union water. Lake Union is fairly clean. It's not like that dirty water that we used to use to just get the experiment to do quickly, but we need to process a lot of water, so our laboratory is near the lake. We set up and ran the water through there. This is the raw water in a white bucket. This is the same amount of water when it came out. It's maybe not so impressive because this isn't so dirty, but still, we're pretty darn pleased. That's looking good. And I want to show you what the tubes look like after they spent, now this is 10 hours of treating water, and on top of exciting science and engineering, it turns out we created art. I don't know how. This is the tube at the end of 10 hours of treatment. The NOM is mostly captured. These are the tubes, and there's a layer of HAPs all around this, the inner surface of this tube. But at certain places, the NOM forms patterns where the color comes through. We really don't know why this is. Something to do with the hydrodynamics. But it's interesting. I don't know how well you can see this. I guess you can see it here. This is the seam of the tube. And these patterns develop right around the seam. So there's something that's going on there that we don't fully understand. But nevertheless, we're getting very, very good water quality, as I showed you in the previous slide. And now I want to show you what happens when we clean these. Remember, these things here have a layer of HAPs on them. The stuff that's not brown is white because of the HAPs. And here's a backwash step when we clean that stuff off. We use air and water. It takes about 15 seconds. And when it's done, these tubes look clean again. These little white spots you're seeing are actually not HAPs, but it's the air bubbles, some of the air bubbles that got stuck in there. And this stuff, let's say we just did this experiment yesterday. We have yet to use these tubes in many multiple cycles, but we're very excited about it because these things really look as clean as when they start. Right? So, oops. Next, we got a contract. But it wasn't because of our great work. I mean, it was because the truth is the UW Civil Engineering Department has, thanks to an earlier benefactor, a very nice connection with people in Norway. There's a former PhD student who was here when I first came, who I got to know, who's now in a position of authority in a consulting firm in Norway. And she said, hey, this stuff you're doing is pretty cool. I have a water treatment plant where I'm wondering if you'd be willing to test it. I said, would I be? Whoa. Yes! And so we built this system now with 60 tubes. We've shipped this to Norway. We haven't yet got it started yet, but that's the core of it. Here's the whole system. Here's one module of 60 tubes. Here's another of 60 tubes. We shipped this whole thing to Norway a few months ago. There have been some startup problems, but we're sure we're going to overcome them, and we're very excited about what to do. And it was around here, well, now a couple years ago, that as Laura told you, I retired. As my wife Judith will tell you, I didn't exactly retire. I retired from teaching. But I have this startup along with some colleagues. And this is what I work on now, is trying to get this technology commercialized. The UW, to my wife's constant consternation, owns the patent on our stuff, which is how it works when you work at UW or for any large entity. And so UW, the good thing is that because they own the patent, they're interested in this technology succeeding. And so a few years ago, they actually paid a business consultant to come in, talk to us, and make some projections about whether we would succeed or not. And I can never say this without laughing. The consultant predicted that within 6 years, we would have revenues of $500 million. We're doing okay. But we decided to hire our own consultants and make a projection, and sure enough, we're actually planning to exceed her projection in a year. Okay. So what can I say in summary? HAPs can be pre-deposited on a porous support, I won't say a membrane anymore, even a mesh, and can collect a large fraction of the NOM from the feed with 1 to 2 backwashing steps per day. Downstream membranes can be operated at high rates with no backwashing for long periods. This is of tremendous interest to membrane professionals, saving energy because of the lower pressures and longer periods. HAP sludge is much easier to dewater and concentrate than conventional water treatment sludge, as I mentioned earlier, a big thing in our favor. I haven't had time, and we only have preliminary data, but it does appear that the process also works for other contaminants such as phosphorus, metals, and some other things. One thing I've learned that I never appreciated before is that scale up is difficult, but it can be immensely satisfying. And speaking of satisfying, there is nothing more satisfying than working with great colleagues. I couldn't possibly list everybody who's worked on this, so I just identified the people who've worked for at least a year or more with me, students and postdocs, some consultants. I've had good funding support. I realize now I actually should add from the UW. They, aside from having that consultant report funded, they also have provided some additional funding to help us commercialize. Here's the MicroHAOPS team. Very impressive. You can see this is Chen-Xiao Kai, a former PhD student, Siamek Motoresi, another PhD student. Al Vetrov's a great project manager that we hired on day one, and we couldn't be happier. We have this slogan that we want to say we change the way water is purified, but just a couple hours ago I said, you know, I got to be honest, let's put a couple more words in there. We hope to change the way water is purified. And then there's this management style issue. With the funding we get, it's funding to commercialize, and so I'm forced to go to various seminars and learn how to be a good manager. I love this cartoon. A startup team requires strong and supportive leadership, and this is, as you can tell from the New Yorker. Here's a team, here's a guy in a little bit of trouble, and the caption says, "So, does anyone else feel their needs aren't being met?" I hope I'm not that kind of manager. But I have to say that in terms of not being thrown over the cliff, the most important person who has helped all these many years and has remarkably not thrown me off a cliff is my wife, Judith, whom I'll be forever grateful. And with that, I want to thank you and open the floor for questions.